Hello, and thanks for joining our presentation on democratizing data. For the first 1/3, we will be going over data modeling and time-aware mirror maker, and then for the last 2/3, I'll be going over continuous integration and Prisma, how we democratize data in practice. But to start, I'll hand this over to Artur, who will be elaborating on our problem and data modeling.
Copernican revolution in data processing is a term introduced by Gordon Everest, 1986, who wrote a book called Database Management. In the same way, Copernicus argued that center of the solar system shift from Earth to the sun, our view of data processing shifts from software to data. The software and data will become more independent of each other, and both are independent of the hardware and closer to people. It took a while, but today we are in the middle of it. We have data-centric manifesto, shifting from application-centric to data-centric view, becoming data-driven, and data penetrates many aspects of our daily work. The reality we were facing was a range of different sources spread across 3 different countries, and all with a slightly different definition of the same concepts. Acquisition of the data would require a deep dive into all the caveats of these sources, so potentially time-consuming and error-prone. We saw a clear need for a platform that would democratize access to that data across the sources without requiring to become expert in each and one of them. We wanted to make it available and easy to traverse for anyone in the organization, even people not necessarily trained in SQL and entity relationship diagrams. This is where the idea of a semantic graph or graph data model was introduced. So we couldn't reuse the sources data models for several reasons. These were built over decades and result of many fixes, workarounds, and compromises, and very source specific. We wanted to abstract that away. And as you know, we can solve any problem by introducing an extra level of indirection. For that, we have chosen Accord. Accord is an industry standard information model, an implementation of semantics technology ability to harmonize entire vertical, segmented by organizations' objectives, processes, languages, locations, and other points of diversity. It provides a uniformity of meaning of heterogeneous data that is widely technology, software, and hardware agnostic. Data in any type of system can communicate with other data with these standards. So design approach that looks at the data entities and their real-world attributes and relationships first. And Accord comes in a range of different formats, either as an entity relationship diagram or UML derivative. Since we wanted to represent this model as a graph, we loaded it into Neo4j using APOC libraries. And it contains a lot of information, but we are only interested in a subset of it. So now we have to identify business entities, attributes, and relationships between them. And so now we arrived and we have at a labeled property graph. And so it has node properties, edge properties, typed nodes, basically the same properties as GraphQL. From that graph, we generate Prisma PSL schema as input to our automated infrastructure pipelines that Lasse will tell you about. So Prisma is a huge technical enabler for us here. Now we have all the necessary components to create a platform that will enable data acquisition across the company. So we gather observations made in the source systems. These are replicated by CDC pipelines and stored on Kafka, our single version of facts. We use GraphQL as an API and common language to interact with the data. And we have Accord that provides context and facilitates interoperability and reusability of the data. And all of these components result in our data broker platform called Tryg 360. This is implemented and runs in production. And we also learned a few things doing it. For example, common language is good, but common understanding is better. So we are looking into techniques like event modeling to sharpen our domain model and facilitate communication collaboration around it, trying to turn Conway's law to our advantage. This also introduces how one can think around events and facts and how they are stored on a timeline. We use Kafka not only as a real-time message broker, but also as a mediator of state that can be replayed at any given point in time. That poses, of course, a few challenges, and Justin will tell you more about it. Personally, I think we should allow more than one model and delegate ownership of it to domain teams and organize API around how it is used, not how it is stored. Thank you.
Here I am going to talk about one of the components in our pipeline called time-aware mermaker. We have introduced this as a solution to one of our critical problem, data synchronization. As you see, we do have a lot of sources, and on top of those sources, there are several data transformation pipelines running. And these streaming pipelines runs with different speeds, meaning some pipeline may finish in minutes, some will take hour, someone will take more than that. Because of that, if we try to get the data from our target at any time, they will give us a wrong data, means it won't give us the current data. So to avoid this problem, we have introduced this TAM. So TAM will make sure all of the data pipeline gets data in correct order based on the time. Also, it will make sure that none of the applications will go faster than others. If TAM sees any of the application is slowing down, then it will make sure that other apps which is going faster take a pause until the slower one in sync with the others. So all the apps moves forward to the target in sync with time and speed. With this approach, we will make sure target has the most recent, current and latest data.
All right, generating a full environment via CI. I'd like to just explain what I mean by that. Here on the left, I've tried to illustrate that we have a lot of different sources. These sources we are loading into a Kafka cluster, a very large cluster. The data loaded in is with all the raw data, so none of the data here has been transformed. It's just laying here waiting to be consumed by us. The data here is actually live streamed in here. So that means when we generate environments, we will also be able to have live data in our environments. Our environments consist of everything inside this purple box. So when we deploy an environment, we deploy time-aware mirror maker, we deploy a local Kafka cluster. What this means is that when we deploy 1, 10, 100 applications, we don't want to load all the data from all the sources. We only want to load the data that our particular application for the environment needs. So this cluster will only contain the data that the particular environment needs, and will of course only deploy the applications that we feel are necessary for this particular environment. A developer might only need a single application or a few applications. When we do performance testing, we might need all of them or a few of them, and for production, of course, we're deploying all the applications that are ready to transform data. So the applications consume data from the Kafka cluster with the synchronized data, and then they transform it and load it into a cockroach database, and then we deploy a Prisma pod that has access to this particular environment's database, and we're able to expose this to users or systems. The way we orchestrate this is we let Kubernetes handle all our resources. We just define them in Helm charts so we can template all of the infrastructure. That means we can auto-scale and we can do a lot of things via templating. And I'll show a little bit what that means. and how we're doing that. But just to reiterate, we want to be able to auto-generate the database based on a schema, and we also want to auto-generate Prisma based on a schema. And then, of course, we wanted to be able to deploy any application or source or combination of those. And of course, we want to be able to do it with a one-click. Why not? So let's have a look. I'll start off with the schema. The Accord model is proprietary, so I can't use it. So therefore, I have prepared 2 dummy Prisma schemas. So here's presentation 1. Oops. With user, post, comment, group, and a dummy model. And if we go back and look at presentation 2, the only difference is that there is no dummy model in the end. That's the only thing. I mentioned earlier that we are using CockroachDB. And as you may know, that's not supported by Prisma at the moment. But CockroachDB is compatible with the PostgreSQL wire protocol, so therefore Prisma is still able to communicate with it. The Prisma CLI is just not able to patch the database. So what we have done is we have set up a pipeline that triggers whenever someone pushes a new file into this repository. This pipeline just pulls the entire repository, checks for any Prisma files, and checks inside Kubernetes where we eventually want to deploy environments, check if the files exist as config maps. If they exist, it just tells us that already existed. If it doesn't, it will add the Prisma file. So you can see here, it's cloning the models repository. It says the config map presentation 1.prisma not found, and then it creates it. And the same for the presentation 2. The other schemas already existed, so it doesn't do anything. And then we use Prisma CLI to actually patch a Postgres database, and then we just extract all the DDL from that. And this we save as a file inside Kubernetes, so that when we spin up our Cockroach database, we can use the extracted SQL to patch the database. That way we have the Prisma schema and the SQL file matching perfectly. So let's create some environments, because this is one click and I just want to show how that works. So here, let's create a random environment or an environment with a random name. We will deploy it into dev. We'll not deploy any applications for this demo. And then we want to deploy this particular environment with the schema named presentation1.prisma. And this is what the pipeline will use to set up Prisma and to patch the database. All the rest here we can change the scale of how large the environment will be. So we use the exact same pipeline for dev, test, and production, so that you don't have something working in dev but not working in production. This way we are sure that whatever we test in dev, the only difference will be the scale of the target environment. So in dev you might have a Cockroach database that is just a single pod, but in production you might have 18 pods to be able to handle the load. So I'll just start this pipeline with the presentation 1 schema. Then I'll create another environment just to show that this is live with a random name. We'll also deploy it to dev. The only difference will be that we will deploy it with a different schema version where we're using presentation 02. So let's run that pipeline, and we'll just do the one-click deploy, play, and when this one is ready, I will say deploy. So let's just have this running in the background for the rest of the presentation. So I mentioned that we are using Helm to deploy it into Kubernetes, and we're able to template all our deployments using that. The reason why that's important is that when we deploy Prisma, for example, we can tell Helm to mount a file into the pod, And that's what we're doing when we are setting up Prisma. We can say that this Prisma pod should just use whatever input we gave when we started the pipeline to determine what config map to mount. And here we're mounting schema presentation 1.prisma into the pod, for example, because we provided the value presentation 1.prisma as the schema version. So this just means that when the Prisma deployment starts up, it will mount that particular one. And if another person uses the pipeline and provides a different version of the schema version, his Prisma pod will simply be using that version. So let me just show the Docker file of Prisma. Here we just start from node 12, and all we do is we add the code of our particular Prisma server, and then we install pal.js. Pal.js is a really cool tool that Ahmed, one of the community members, made, and this is able to auto-generate resolvers and type definitions based off a schema. So this is a large part of our infrastructure, what is making it possible for us to have an automated infrastructure. Then we run a script, entrypoint.sh here, and then we just run yarn dev. So let's have a look at the entry point. What it does is it just allows us to do development on Prisma locally. So if we run it inside Kubernetes, there will be a file in the mounted directory, in which case it will just prepend the schema file. So it will take all this text inside the Prisma file, and then it will just prepend this text here, which is necessary for the Prisma client, so that when you run Prisma generate, it knows what to generate and what data source provider you're using and what the URL for the database is. Let's just keep this running in the background. Yeah, and in the end, it will just install any dependencies that we have. Then it will run yarn generate, which is actually just Prisma generate. And let me find the entry point again. Then it will run palg, and this is what will auto-generate our resolvers and type definitions based off the schema, and then it will just start our Prisma server. Yeah, so hopefully our deployment is done. It is. Took 3 minutes, but now we have it. So all the infrastructure that I showed you before should be available to us, at least the Prisma part and the database part, since we are not really interested in the loading applications and Kafka and so on. So let's just have a look. If I say get config map, so what I'm doing here is I use kubectl CLI for Kubernetes to just ask Kubernetes, give me all the config maps. And here you can see that we have the presentation 1.prisma and .sql that was generated by the pipeline. And if I similarly say, show me all the pods running in this particular namespace that my alias is pointing to, I can say grep Prisma, and our developers have a lot of environments running, so I'll probably have to take a look at what I called my environment, called RDR. I think that's, I have to grep RDR. So here's a Prisma pod. You can see it's been running for 111 seconds. And let's just have a look at that, what is going on. So yeah, fun fact, the schema files that we have, they are over 10,000 lines long. They are over 1 million characters long, and Kubernetes doesn't support that large config map. So we have to compress our schemas before we add them to Kubernetes. So our pipeline also does that. And then we decompress them inside the Prisma, but that's why it says compressed. We install all the dependencies. We generate the Prisma client. So that was Jan and Jan generate, and then PLG. So here we generate all the type definitions and resolvers for the particular schema, and then we start our server. And another cool thing that we set up in our pipeline is that whenever the deployment is done, it shows us that we've deployed to dev to this environment, and I can click on it, and I can see that it was created 6 minutes ago, and I can open the live environment. And here we should be able to query the model that we set up. So find many, and you can see here I have, let me just make it larger. You can see I have find many dummy. If I go to our other pipeline, looks like it's also done. Let's just go to the top, go to the environment, open it, and here we shouldn't have dummy. So if I say find many dummy, you can see it doesn't really autocomplete to it, and if I try to select anything from it, it says it doesn't exist. But if I ran this on the environment where we used the model that had it, you can see that it actually finds it, and you can see that it actually does have connection to the database. There just isn't there isn't any data in the database. If we take a look at the inside the pod, I'll just bash into it. So now we're inside the pod that's running in Kubernetes, and I can go to source GraphQL, where we have the resolvers. You can see that PLGS has generated resolvers for all the models that we had defined. So you can see if I cat comment /resolvers that they have been automatically generated. And this is exactly the same thing we do when we run our real environments. Of course, we just use different schemas. And this is what allows us to democratize data. We will have a very quick development cycle where a developer will be able to spin up an environment at the click of a button, call it whatever he wants, deploy the applications that he wants. He'll be able to look at the data after it's been loaded. He'll be able to check it live. He'll be able to share the URL with a user perhaps that has to verify it. And this just makes it for very fast iterations, because if you had to set up environments manually, or you had to wait a long time for any load to happen, you can imagine with as complex a model that we are using, with as much data as we need to load, it would simply take too much time to get close to a finished product if you didn't have a setup that would allow you to generate everything. So we are very happy that we went with Prisma and CockroachDB, as they enable us to generate everything based on code. And that's all we had for you today. So thanks for joining. Hope you found it interesting, and have a nice day.
We're back now for a live Q&A. Thank you again, Artur, Justin, and Lasse. That was a very insightful talk. In particular, the application of theory, its application in democratizing data at Tryg, and the role that Prisma played along in that journey. So we're now going to start this live Q&A, and if you have any questions, please feel free to shoot them via Slack channel. And now to sort of open up this Q&A, I'll start with a question to you, Artur. So you mentioned how common language is good, but common understanding is better. How do you achieve this in a large organization with multiple teams focused on different domains?
Yeah, good question, and it is of course a challenge. And we try to harness opinions and perspective across the organization, trying to create cross-functional teams and basically involving people in creating the data products in data analytics. So rather than creating something for them, we create it together with them.
I see. And in your talk, you described how you created essentially this Tryg 360 platform to enable data acquisition across the organization. And you've used a variety of different technologies and techniques, for example, CDC, which is change data capture, Kafka, GraphQL, and Prisma. And I'm curious to hear, what were some of the challenges that you faced in the design of this architecture? And I assume that there was also a lot of legacy technology that you had to sort of deal with in creating this new platform.
There was the whole solution has been through quite a lot of iterations. There was a lot of testing going on with different databases. We also tested out Hasura, and we tested the performance of different parts of the infrastructure, because when you need to load that much data, it's important that it doesn't take half a year or take a very long time. So a lot of our time was actually spent testing out different technologies. And with databases, we found that their reliance on disk I/O on a single master, for example, was just a no-go for us. We just couldn't get the throughput we needed. And then for me, personally, one of the challenges was to automate everything into one button, so that once we want to enable our developers to be able to have a very easy and quick cycle. So when they need to use a new schema, when a new model comes out, we want to make it easy for them to develop their applications. So deploying a Cockroach database and the Kafka cluster and automating the GraphQL code and everything at the click of a button and parameterizing everything, that was also a bit of a challenge.
Quite the undertaking, but it looked, based on your demo, it looked quite impressive, just going from a single click and a couple of parameters to a working environment. Moving on to the next question. If I understood correctly, the time-aware mirror maker essentially solves the problem of incorrect data due to synchronization disparities between the different data sources that you're essentially putting together in this Tryg 360 platform. And you're doing that by relying on time. Does this mean that synchronization latency will be determined by the slowest transformation pipeline?
Yeah, it's actually happening in two ways, actually. The first one is, of course, the time. We will only copy the data based on the timestamp. And of course, the next one we are considering the fact is the latency of any data pipelines. Because if there is a data pipelines which has huge data set, means in a second, if it is getting more than 10,000 or 20,000 records, and it just doesn't make any sense that other pipelines which is faster should complete. So based on the slowest one, we just make sure that everything goes in a synchronized way. And obviously, we are just making sure that there is no slow runners. Even if you have a lot of data, we just make sure that it runs faster.
I see. So does this approach, would you say that this approach favors consistency at potentially the cost of some latency?
Yeah, you can say that. We just actually wanted the consistency actually. So yeah, when you say at cost of time, yeah, obviously as I mentioned earlier, we just make sure that there is no slow runners in our data pipelines.
I see. So I guess these are constantly monitored to ensure that this doesn't happen.
Yeah, exactly.
Okay, well, I would like to thank the three of you. It's been really insightful to learn about your journey using Prisma and about Tryg's architecture. So thank you so much, Artur, Justin, and Lasse, and I hope to see you soon.
Thank you.
Yeah, thank you.
All right.